Greetings and welcome to the video explanation of the Material Science Toast Testing Lab. So there is a protocol online that is available, but it might help to see a video of how this is intended to be done, with a few extra indications of why I may have put a couple things in that protocol. So the first thing we want to look at is the setup. Now, most of you, or all of you, should have already received this toast testing contraption, the apparatus here. And as shown before, we have a carriage with a hammer. And then the rest of this is, you've got the upper portion here that the carriage rides on, the rails. This keeps the rails more or less in place. And then there's the rest of this making a 3-point loading structure. Now we have some sample bread here, a little squishy. No, that's toy bread. And you just put it in here. And then this does a 3-point bending test to failure. All right, so that's the basic setup of it all. Now, how do we load it carefully and consistently? Well, we have a box here, very high-tech box that is placed in there, and we have an array of currency here that will load it and get heavier and heavier so that eventually the toast breaks. So that's the basic setup. Now, when you have this, depending on what you've done with it or whatever, you might need to make some very minor adjustments. So one of which is to make sure that these parts here don't run into these side beams. So you want them to clear the side beams here and there. If they're out of whack, you'll hear a little clicking. Okay, it clicked enough that it pushed itself back, but if you hear some clicking, okay, you might want to adjust those things so that they're clearing those sides. All right, so that's one thing. And also helping that, all you have to do is take these side beams and pull on them just a little bit. Like this. Take these blue ones and pull on them a little bit. That'll give you probably just enough clearance to make it work really well. From time to time, when this gets really heavy, it may actually break something off. Now, don't worry about that. But these things, it's very difficult to actually break them. So, but it might come apart a little bit here. Just snap it back into place. One thing that might come off is this thing. This thing is here to just support this. It's not structurally critical, but it is important so that the weight is evenly distributed. So it just pops back on like this, but it's also intended that it rides inside these parts here. So you want to make sure that it gets back into place there. It'll be held in place pretty well there. That's probably another spot. So maybe these things come apart a little bit here and there, but again, you pop it out like that, pop it back in like that. Should be pretty easy. All right. So that's the setup. So next, that's the setup of the machine itself. Let's look at how we put in our toast. There we go. So that's riding a little better. So I have a real piece of toast, toasted about 5 minutes here. This is not the official bread because you guys took all of that from me. So I'm going to put it right here in between these two parts and make sure that it's centered as best you can here. Okay, we want to make sure that the load is completely distributed on this as best as possible and it isn't to one side or the other. I have noticed that if the toast is a little bit funny, you'll see differences in deflection from one side to the other. So we try to minimize that as best we can. So putting it here and noticing that it is fairly symmetric here and here. This toast is a little bit too short. Yours should be wider, and it shouldn't be critical that it's perfectly, absolutely symmetric, whereas this one is a little bit too, not quite wide enough, so I've got to really make sure it's exactly in the middle. Okay, so I've got this toast properly placed in here. Next, I want to show you how to do the measurement. Now this, if you watch nothing else on this video, this is what you want to watch. Okay. What you want are two consistent flat pieces that are going to be consistent all the way down. Some of these pieces are not properly symmetric. So you want to be looking from the top of this white connector to the underside of this one. That's the best I can do for you at this point in time. I could have done some other things, but this is the best we can do. And as you do this measurement, you have to be very, very careful, because we can measure to the thousandth of an inch. But if you pull up too far, you will actually lift up the carriage. See how I'm lifting up the carriage like that? So you have to make sure that you don't lift it. In fact, you can lift it to the point where it kind of gets stuck in another position. Because the carriage is not perfectly going up and down. It's plastic toys. So that's why we have to do two measurements. So you want to measure that distance, and you want to do this before you load any quarters in here, because this is the most important distance, is the measurement from here to here. And then all other measurements are going to be deflection, what the change is from this. Okay, so I end up with 1.767 inches. All right, you can use millimeters if you like, but 1.767 inches. And so you should have a notebook, or you can enter it directly in on your computer at that point in time. Now, you also don't want to move the setup while you're doing the test, but I'm going to anyway so that the camera can see it, but you shouldn't do it. You want to measure the other corner, because this carriage can rock back and forth a little bit depending on what you've done. So be very, very careful not to rock it, not to move it. And, because as you're measuring the one side, you can knock it off kilter a little bit. But if you do, that means the other side would have compensated. So I'm going to measure that as well. And I'm keeping my head out of there for the sake of the camera. And I get 1.718. The reason why I did this, at first, I was just going to measure the one side, but I got some really wonky readings. So, it would go up, or, it would show clearly that it was going down, and I'd put more coins on, and you would expect it to go down further, but it actually went up or stayed the same or something weird. And I realized it was the shifting of the carriage that had that. Once I instituted double measuring one corner and, the far corner and the near corner, my numbers kind of averaged, right out. It worked out a lot better. So that's why we have to measure both one side and the other to get good data. Okay, so the measuring part, I can't express how important it is to be super duper careful. Now, I also found that to make it easier was to have some kind of light in the background or dark in the background, something like that was easy. And if you've got some kind of crazy background, it's harder to do. But you don't want to rest it. You don't want to sit there and rest it on the upper carriage. You can rest it on the lower part, that's fine. But going up to the upper carriage. So again, now it's 1.787. And before I measured it, it was 1.767. So you can see that my messing around definitely made a difference. That's, again, very, very important. Let's load a few of these. And so the placement of these quarters is not terribly critical. You want to start off with them in the middle, okay? But it's also a good idea just to kind of spread them out. All right, so I put 10 in, and honestly, don't expect a lot right off the bat. The first few measurements are going to be a little wonky. Okay, oh, maybe not. This one ended up being 1.760. I put this in the wrong place already. 1.760. And then the far side is 1.6. I got to try that again. Did I do that right? Okay, that's a little better. 1.721. Yeah, it was hard to do it from that angle. So you got to get a good angle on it, and you got to be super duper careful. Okay, and that's as simple as you need. That's all you need to do for each one here. And so then that was at 10. So if you'll notice, the far one actually went up. In other words, it got further apart. So that's kind of wonky. And the lower one only went down 7 thousandths of an inch. So on average, we went up 3, down 7. So on average, that's what? We went down 2. So we put another 10 coins in. And when you put them in, don't drop them, boom, because that's going to make a difference, especially with brittle materials like that. All right, so... yeah, try not to move it. I'm doing a bad job there. So I got 1.762. I actually have a pretty good background over there with that that light coming through, so I can really see it when it touches. This is 1.7. So one side went up, the other side went down. So I practically went nothing on that one. But eventually you will see significant differences. Okay, so again, I'm putting these in carefully, kind of central. Right now I'm hearing some cracking and crunching, so I'm not sure. I think we're close though. Okay, I just heard a big crack there. Or not big, but a large. So it was about 240, 250 quarters that this failed. We had to cut out for various reasons, but we actually caught that on video, which was kind of neat. Now, the next thing that you need to do is remove all of this. Okay. And you should take the picture that I was showing you before. Okay, so I got a picture like that. So after that fractured and you took the picture, what you want to do is look at the material itself. Notice how this one's still connected. If you go to some of the more brittle ones, they will have completely fractured. So make a note of how these things look after the test is done. So to that end, you should be labeling them. So you take a plastic bag and you write 5 minutes, number 1, something like that. Whatever minutes works for you guys. Open it up, put this in to label it and keep things neat because you're going to get a lot of stuff all over the place here. All right, then you can use them and compare. So I did that over here with my original bunch here. And if you'll notice on this one, it's all fairly well connected. 10 minutes, it's not, it's obviously more brittle. 15 minutes, definitely a clean break. And if you want to see 20 minutes, okay, yeah, that was pretty brittle. It just collapsed there. So it makes those material observations of the different ways in which they break, not just the numbers, although the numbers will tell you something too. Speaking of the numbers of this one, if you do follow them along here, you'll see that I did have a general trend towards displacement. So 1.767 there, down to 1.678. So between here and here is a full 1/10 of an inch of deflection. Now, sometimes it went up and down, this and that, but this doing the average from near to far is going to make a big difference in how smooth your data is. And then averaging between them is also going to make a difference. So when you actually do your deflection on your spreadsheet, you're going to want to subtract the average of this, in this case, I don't know, 1.74 or whatever it is, from all the rest of them, their averages as well, so that you know the actual deflection. So the deflection for 0 is going to be 0, and everything else is going to be something different. It's going to be the subtracting that one. So here we end up. If you'll notice, I took some notes. Here, there's a cracking sound, or was it coin moving? I'm not quite sure, but I definitely heard some cracking here, and there were little bits and cracks all the way here, and then at 250, I wasn't able to fully measure it, and it failed. So those are the observations you might want to be working with, and make sure you keep your samples and label them. Now, one thing I really like about this whole experiment is that it really brings into the, it brings into a lot of things, that. I forgot that it was going to slip out this way. It's what happens when you don't have bread there. Anyway, this is actually a distributed load like we studied in statics and on beams. This becomes a beam, and it's a distributed load across here, which eventually transfers its distributed load to this beam, but it does it in point loads. And hopefully it's well distributed along this beam, which lends its load to the toast, which itself becomes a beam of, in this case, 3 points. And this whole entire structure is also a structure that you may have studied in something like statics. Obviously, strength of materials comes into play, and some of the deflections in here of these various things, and the deflection of this is definitely part of strength of materials. And this whole thing is based around material science. But not only that, I used Lean Six Sigma to lay out everything and make sure everything was planned out so that everything went fairly smoothly, with the exception of what just happened here. Okay, so it's neat to bring kind of a whole lot of your education together in one experiment there. So in summary, we have this experiment where we can use household materials and some toy-like things that can do a 3-point bending test on bread and actually get some decent data here. So here's an example of my 5-minute and my 10-minute toast test, and notice how the average line bumps up a little bit. 5-minute didn't last very long, but 10-minute did, and that's for the other bread. This bread would seem to be a lot stronger. Also, this bread had been frozen, so the outsides were more toasted than the inside, and they got toasted more instead of having them all even. So make sure everything is as consistent as possible. You should have refrigerated bread rather than frozen bread like I did. Okay. One last time, I want to emphasize how important it is to carefully measure everything and barely touch the top and not move everything while you are doing the measurements, because otherwise your data just really won't be that great. And you don't want to be just writing a lab report that says at the very end, I just didn't take good care, and so I didn't get good data, so I can't really understand what's going on in the lab. So taking that time, taking the care will yield really good results in the end. All right, I hope this really helped, and enjoy that, and make sure you at least have a couple slices with some butter.